Welcome back, and in this video we will just visit some introductory thoughts about supervised learning models. Here you can see the overview, what we are going to do within the next videos. We start with quite basic models, but I think this is an important step to understand these models because the principles we're learning here can also be applied to more sophisticated models. And also these models can be seen as building blocks for more advanced models. All right, before we do anything, let's quickly talk about notation, which makes it easier for you to follow the explanations, especially if they are provided to you in a formal way. And usually we'll have a data sample. It's also usually structured, so-called structured data sample, which means we have certain units that we're interested in. For instance, it could be persons, or it could be objects like houses or anything. And we will collect information about these units, and the information is collected by variables. So, for instance, the age of a person, how much the person's income is, and so on. And of course, then we'll have concrete realizations of the variables. These will be our data samples. And if we take a look at a complete data sample, so this means the realizations for the variables of interest for a certain amount of units, we will shorten this by this bold, a big capital, typically an X, for which is the data set, so it's a matrix. If we're talking about, like either a row of this matrix, which corresponds to the realizations of a single unit, or the variable, for instance, like the age of all people or all houses in a data set, we will use small bold letters, and these are the abbreviations for vectors. Then the concrete realizations are given by the lowercase letters, as you can see here. And here, I also need to, or for the sake of completeness, usually we would distinguish here between like the big capital letters and the small ones, and distinguish this in order to, declare if it's like if we're talking about the random variable in general, which is then typically done by the big letter or by the uppercase letter. And if we're talking about the realization, this is usually indicated by the lower capital letter. And even though statistics may really not be, may not like this, but just to make it easier for you and to keep the notation more simple, I will not distinguish here in my slides. So no matter if it's like the random variable or the concrete realization, I will always use the lowercase letters. So big sorry to all the statistic experts here. All right. Usually, especially in this chapter, we talk about supervised learning. Supervised learning means that there is a target variable, which often also needs to be labeled manually by us. And usually we will use the Y letter for declaring the target variable, and the X for the so-called predictor variables or independent variables or feature variables. So these variables are supposed to provide the information to us in order to make predictions about the target variable. And we will use an I and a J. These indexes, the I corresponds to the ith observation, so the rows in the data matrix, and the J corresponds to each variables, so the columns in the data matrix. All right, that's it with respect to notation. Just make sure to come back here if you see some formal declarations on the later slides, and if you are not sure about the notation, because if you're really aware of it, it will make it much more easier for you to understand the formal notation and the declarations of the models in the upcoming slides. But just here like a short example. So for instance, if you're interested in the amount of sold scoops from an ice cream stand, a data set may look like this. So this would be our data matrix X. We collect the variables temperature, the weekday, and also the target variable, so the sold scoops. So now, for instance, for the temperature, we can use the numbers as they are, and we'll come also to this, what we're doing here later, but for now, assume we have like category feature variables, for, like here the weekday. We will calculate with, or we're supposed to calculate with these values. So we always need to transform categories into numbers, and one way is to use so-called hot encoding. And as the name suggests, we have a 1 where it's hot, so where the corresponding category is given, and 0 otherwise. So for instance, this could be the Monday, the Tuesday, the Wednesday, the Thursday, the Friday, the Saturday, and the Sunday. And as in the first row we have a Wednesday, we have here at this point a 1. So this is how our data matrix would look like, and then we would have the vector with the data, with the target variable, which are the sold scoops in this data set. Okay, so now very generally speaking, there are many things all the models have in common. So typically when we are in supervised learning, the idea is that we have certain variables, which are the feature variables, and that we assume that there is at least to a certain degree some kind of deterministic relationship to the target variable. So statistically speaking, we are always in a conditional perspective. So given we observe these certain realizations of the feature variables, what is our expectation, for instance, what we expect about the target variable. And only if these feature variables are in some way related to the target variable, a model can succeed by providing good predictions about the target variable. I hope this intuitively makes sense to you. So we always will develop models of this form, like some sort of functional relationship, and the input is given by the feature variables, and this outputs a prediction for the target variable. And of course, only in the best case, and only if there is really like a complete deterministic relationship, the prediction is going to be exact the same value as the true realization that we observe in reality. But this is usually not the case, so there is usually some deviation between the prediction and the actual realization. And the reason for this is also that usually there are no complete deterministic relationships between the feature variables and the target variable. Always there is some randomness which comes into the models, and randomness can be interpreted in many things. It can be really like true randomness, but also randomness can be can originate from the missing of additional feature variables which would be helpful in order to really find the deterministic relationship. Okay, but that's not so important right now. The most important part is that you really understand that we are typically trying to make a conditional prediction, conditional on the information which is given by the feature variables. We're trying to predict something about the target variable, and for this, to fulfill this task, we aim to find an appropriate function, so an appropriate functional relationship between the feature variables and the prediction. So most common are so-called regression or classification problems. When we talk about regression problems, we usually mean that the target variable is an unbounded or usually unbounded numerical variable. And when we speak of classification, we either mean like a binary classification problem, so yes or no decisions, or also multi-classification problems, so where the target variable can have more than 2 categories. Okay, these functions, they usually are defined by additional parameters. So the parameters are usually our way to calibrate the functional relationship. So this is why we indicate this usually by in the subscript giving here a vector theta, which is supposed to include the whole set of parameters that are used to declare the functional relationship that we are using to generate the predictions. Okay, so and then what we also need, so we will not go into detail here about the concrete functional relationship. This is for later stages. In this video, assume we have some sort of function that we are going to use. And now what we also obviously need is a way to evaluate if the predictions for the target variable are good or bad predictions. And usually we evaluate this with a so-called cost or loss function, especially in the progress of calibrating the functional relationship. And the cost or loss function, as the name suggests, is the cost that comes along with mispredictions. So that means the worse the predictions are, the higher the cost or the loss values are. So what we usually have is we have like a data set including multiple samples, and usually we try to estimate the model on the basis of all the samples or a subsample of the data. And we then compare like the predictions from our model with the actual realizations, and we plug in the realizations and the predictions into a function, and this value, the lower it is, the better it is, because the least costs we have, and least cost means that our predictions are close to the actual realizations. So this is like the general principle. And this is what we need in order to get some feedback if we already succeed in calibrating a reasonable functional relationship between the feature variables and in order to generate the predictions, which obviously have the aim to be close to the target variables. Okay, so if we resume this, or if we subsume here, then what you really should remember right now is in the area of supervised learning, our aim is to generate good predictions for a target variable. We assume that there are some variables which help us to generate these predictions. So that is indirectly we assume that there is some sort of relationship which is at least partially deterministic between the feature variables and the target variable. And we will use a function which depends on parameters in order to calibrate this relationship. And we use a loss function, so it's another function into which we plug in our predictions and the actual realizations, and which will then provide us feedback if the calibration of our function, which is used to generate the predictions, is good or bad. So if the predictions we're making are good or bad. Okay, and so if we do this, obviously our first aim is like to make good predictions, but this is not the only aim, because in our mind we also have the idea, if we find the relationships here between the feature variables and the target variable, then we can learn a lot about the data and about the relationship in general. So we always have the aim for our model to generalize. This means, of course, we always use with samples of data. So, like we collect some random sampled data, and then we will calibrate our model and do our best that this calibration is good. But obviously, the model is only good if it also works well for new and unseen data. And only if this is true, then we succeed in finding a model which generalizes well. So this is an important aspect which you should be aware of, and which you also need to know when we later talk about aspects like overfitting and underfitting. And in addition to that, like we already have a cost or loss function that we use to calibrate the model, and which can be seen as a feedback if we have good predictions or not. But additionally, we also can use further metrics in order to validate how well our model fulfills this need for generalization in order to provide really good results for seen and unseen data. And once we really succeed here, then of course we can find out more. Then we can use our model to learn about the relationships within the data, not only to generate good predictions. We can also ask questions like, okay, by which feature variables are our predictions driven the most? Can we find any interactions among the feature variables? are the relationships between the feature variable and the target variable, are they rather linear, are they nonlinear? These are all very important insights into data and into the relationships between our variables of interest, and this can also be seen like as a bigger aim besides only generating good predictions. Okay, so this is like the very general perspective, and now we approach this with examples from a modeling perspective. So in the next subsection, we use, I would say, like basic or ground models that can be used for regression type problems, for binary classification, or for multi-classification problems. And we always revisit those models from the aspects that we discussed so far. So we always define a function which depends on parameters and is used for generating predictions for a target variable. Then we will define an appropriate loss function in order to calibrate the parameters of the model. And then we will take a look how well we can, use this to set up models that hopefully generalize. All right, and after this, so we now will do this quite quickly, just that you quickly get an idea how the typically model approach works for different kind of target variables. And after that, we will dig deeper a little bit, especially, like how are we going to estimate the models? Like we will take a look at gradient-based optimization, which can be used for all these different models and other model types, and in general also discuss things that are important to know and to be aware of, like upsampling, downsampling, cross-validation, underfitting, overfitting, and so on. So these are just like the roadmap for the next videos, and of course after that we will dig deeper into more advanced models and also approach the area of unsupervised learning. We do this in the next videos, so hope to see you soon and have a good time until then.